Hello everyone, welcome to the video demonstration of our control system theory project. The topic of our project is physics of a PN diode. At first, I will explain how a PN junction is formed, that is the basic structure of a PN junction diode. This is a bulk of material. It can be made of any type of material. For our case, we have considered it to be silicon. On the left hand side, we have put some p-type doping, and on the right hand side, we have put n-type doping agents. So the region on the left has got acceptor ions, and the region on the right has got donor ions in it. So this, after the formation of this, some of the holes in this region, some of the holes in the p-type region will diffuse to the n-type region, and some of the electrons in the n-type region will diffuse to the p-type region. So what happens then? We have got the p-type region here, same as before. We have got the n-type region here, same as this one. This is our boundary line. Some of the holes from this region will diffuse to this region. Some of the electrons from this region will diffuse and come to this region. As a result, an electric field is formed here. This electric field direction will be from the positive charge to the negative charge, and this region is called the space charge region. In short, it can be termed as SCR. This is how a basic PN junction diode is formed, and thereafter we will be explaining the topics we are going to cover in our present video demonstration. At first, we will plot the space charge density in the space charge region. Then we will plot the electric field followed by the potential. Thereafter, we will be plotting the energy band diagram of a PN junction diode with respect to different doping concentrations and as well as with respect to different bias applied. From the second diagram, we will obtain the quasi-Fermi level of the PN junction diode for electron and holes. And finally, in our video demonstration, we will plot the IV curve of a diode. Let us take you to the MATLAB demonstration of our project. So this is our MATLAB code. We have added a lot of comments in our code so that you can understand our code easily. For better understanding, we have also built our own graphical user interface. When you run the code, you will be able to see the graphical user interface. In the description section of our video demonstration, you will be able to find these codes which we have used in our video demonstration. So now let us run our code. This is our graphical user interface. At the bottom you can see the region to apply p-type doping, and on the right you can see the region to apply n-type doping. We will at the very beginning apply some p-type doping. Now we will apply some n-type doping. So at the top of the screen you can see the plot. You can see the plot for space charge region. The region on the left is the p-type region. Region on the right is the n-type region, and the region in the middle is the space charge region. Thereafter, in the second plot, you can see the space charge density in the space charge region. The third plot gives us the electric field in the space charge region, and the fourth plot gives us the potential in the space charge region. You can also change these doping concentrations by pressing on the sliders, and you can also change the doping concentration on the n-type region. So you can vary these doping concentrations, and you will instantly observe that these curves will change accordingly. So this is our second code. Here we have plotted the energy band diagram with respect to different doping concentrations in the p-type and in the n-type region of a PN junction diode. This code is also self-explanatory. So now let us run the code. This is our graphical user interface for the code. In the bottom you can see the region to apply p-type doping, and on the right the region to apply n-type doping. At the very beginning we will apply some p-type doping. Then we will apply some n-type doping. So this is the curve we obtained. This is the energy band diagram when we apply different doping concentrations in the p-type region and in the n-type region. You can vary these doping concentrations and observe the effects of observe their effects on the energy band diagram of the PN junction diode. And this dotted line in the middle is our Fermi level, as you can see, and the legends are given here for better understanding. So this is our third code. This is almost same as the second one. The only difference is that we have varied the bias voltage applied, and we have kept the doping concentrations in the p-type and n-type region on a constant level. So now let us run the code. This is the user interface. On the bottom you can see the region to apply the bias voltage. We will apply some reverse bias voltage here. So as we apply the reverse bias voltage and we change it, we observe that the energy band diagram changes with it. The legends are given here so that you can easily understand which curve plots what. The red one is our quasi-Fermi level. This curve can be further varied by changing the bias voltage applied to the PN junction diode. You can also find the procedure to apply forward. You can also find the procedure to apply the forward bias voltage in the comment section. This can be done very easily by changing a parameter. This is our final code. Here we have plotted the IV characteristics of a PN junction diode. The material which we have used is silicon with a voltage threshold of 0.7 and Zener breakdown voltage of -5.6. In the reverse bias region we have considered the resistance to be 10k. You can change it as per your likings. So now we will run our code. This is the curve we obtain when we run our code. The region on the right from 0 onwards, this is the forward bias region, and from 0 to the left, this is the reverse bias region. Let us first explain the forward bias region. At a voltage of 0.7, you can see that the current through the diode increases sharply. So this is the threshold voltage, and on the left at a voltage of -5.6, you can see that the current increases enormously. So we can understand that the diode has reached its Zener breakdown voltage. So that is all from our part. This was our final code. Thank you all.